things about absolute values and distances. And the thing I want to emphasize first is just this line in which we said exactly how to compute absolute value in like a case-by-case basis. If you have a number x, well, that number is either positive or negative or 0. If that number is positive, absolute value doesn't do anything, it leaves it alone. If that number is 0, absolute value returns 0. If it's negative, you want to make it positive. How do you make a negative positive? Well, a double negative becomes positive, so you stick an extra negative. And this is a particular type of function that we'll see a few times throughout the class called a piecewise function, or a case-wise function sometimes. So a piecewise function is a function that has different formulas depending on what type of input you have. It has different pieces. So in the case of absolute value of x, well, when x is positive, we just said absolute value of x is x. When x is 0, absolute value of x is 0. When x is negative, absolute value of x is negative x. And let's just describe how to read this notation. This notation says if you have a number you want to compute its absolute value, step 1, ask yourself which of these cases you live in. Either this number is positive or negative or 0, figure out which. Once you know that, this tells you which formula to use. And let's do exactly that. Let's maybe even, let's start at 2. Let's try to use that idea to compute the absolute value of pi minus 4. And to do that, ask yourself, pi minus 4, is that positive, negative, or 0? Negative. Cool. Pi minus 4 is less than 0. So which of the 3 cases do we sit in? The first, second, or third? Third. So we should use this bottom formula. Pi minus 4 is the same as negative pi minus 4. And in some sense, this satisfies the point. There are now no absolute value values left in that expression. Does that look like something that should simplify? Yeah, let's distribute that negative. This will become negative pi, double negative becomes positive. And I don't know, I'd want to do one other thing to write it in a simpler way. That's the same as pi minus, as 4 minus pi. Cool. Yeah, just, especially if you're planning on using an answer later on, you should simplify it. That idea seems sensible? Nice. So let's just talk about nested expressions really quick. So let's suppose you wanted to compute this one. The absolute value of 5 minus the absolute value of 1 minus 7. That look like something we can do? Yeah. I guess the way to do it is from the inside out. Let's start with 1 minus 7, and let's include the absolute values too. What's the absolute value of 1 minus 7? 6. Because, right, 1 minus 7 is negative 6. Absolute value of that is positive 6. So this will become the same thing as absolute value 5 minus 6. Maybe just to help with what is equal to what, those two underlined things are equal to each other. Well, all right then. Now it becomes easier, right? What's 5 minus 6? Negative 1. And then the absolute value will make it 1. So if you see a complicated nested expression, just evaluate one piece at a time. Seem okay? All right. And then I guess remember all the order of operations things you already know. Let's go back to this idea of absolute value as a piecewise function, evaluating depending on which piece is appropriate. Let's suppose I tell you this. X is a number, it's greater than 7. Tell me, then, what is the absolute value of x minus 7 without any absolute value? Just x minus 7 again? Yeah. Why x minus 7? What was the reasoning? Yeah. The thing in the absolute value is positive. Absolute value doesn't do anything to positive, so it returns the exact same thing. So if x is greater than 7, x minus 7 is bigger than 0, so absolute value doesn't do anything. All right, so that gives us this now algebraic doodad, the absolute value function, which has the function of erasing negative signs. If you see a negative, absolute value makes it positive. It has a geometric meaning. It computes distance. And in order to see it computes distance, well, let's just see. Let's try to geometrically first compute the distance from -3 to 2. There's -3. There's 2. Just by eyeballing that number line, what's the distance between them? 5, right? Yeah, you have to go right by 5. There's a formulaic way to compute the distance between two numbers. So the most instinctive thing to do would be to that's like the difference between them, right? What would be wrong with calling that the distance between these two numbers? Yeah, it could be negative, right? If I had the x and y in the long order, maybe it's negative. Oh, so I just want to make it positive. What's the thing that takes a negative and makes it positive? Great. If I give you two numbers and want the distance between them, just take the difference, take the absolute value. So let's try to use that. If you use that formula, let's compute the distance from -3 to 2 using it. So that should be the absolute value of -3 minus 2. Is that equal to 5? Yeah. Thing in the absolute value is -5, it becomes positive. And so let's, just to practice with unraveling definitions, do one example. So let's take this statement and translate it to an inequality with some symbols. So let's suppose I tell you that y is a number, x is a number, and the distance between x and 2.5 is less than or equal to 5. How would you translate that to an inequality with some absolute values? Let's think about it one piece at a time. I see this bit is less than or equal to 0.5. Something is less than or equal to 0.5. And what is that something? It's the distance from x to 2.5. Absolute value x minus 2.5? Yeah. If you see some string of words that has something that you have a mathematical definition of, use that mathematical definition. The distance between x and 2.5, well, the distance between any two numbers is the absolute value of the difference. Take the difference, throw the absolute value around them. That is less than or equal to 0.5. Nice. Many people instead would have wanted to write down 2.5 minus x in absolute value. Yeah, well, it wouldn't have been wrong, would it? Distance between two numbers, it doesn't matter what order they're listed in, it'll be the same. And absolute value does that job. Neato. So one last thing in this particular pack. Let's solve some equations. Let's solve this equation. And maybe I'll do this one of two ways. If you were to see that equation, does that look like something that you know how to solve? And maybe I'll ask this, how many people would like me to talk through before I have you do an example? People want me to talk? Okay, I'll talk. If you want to just go through it on your own and see if you write things that are more or less the same as what I write, great. Otherwise, let's go. So you want to solve this equation. Absolute x plus 5 minus 7 equals 3. So one strategy when solving an equation for x is you want to get x on its own. You want to turn this thing into just x equals. And so one way to think is let's look at the last thing you do starting with x and undo it. You start with x, you add 5, then you take the absolute value, then you subtract 7. So the last thing you do is subtracting 7. What undoes subtracting 7? Adding 7. Let's add 7 to both sides. Anyway, there's no deep idea there. But it's nice to, say all the wads about why this is a reasonable thing to do. That'll give you absolute value x plus 5 equals 10, I think. All right. Absolute value x plus 5 equals 10. So what we see here is absolute value of something equals 10. What numbers are allowed to have absolute value? If I tell you a number has absolute value equal to 10, what could that number be? Negative 10, or it could be 10. Right? It couldn't be like negative 17, because that would have absolute value 17. It couldn't be like 3, it would have the wrong absolute value. So it could be 10 or negative 10. Here is the idea that is being used here. If you see absolute value set equal to a number, if you see some stuff in an absolute value, you can get rid of the absolute value and set equal to something. You can get rid of that absolute value by saying, well, that star could be equal to either that something or minus that something. But there's maybe one thing wrong with that. Let's suppose that instead we wound up with like a negative 10 there instead. What numbers have absolute value equal to negative 10? Yeah, you're shaking your head. Why? Awesome. Absolute values cannot be negative. If C is negative, absolute value of star equals C has no solutions. So whenever you get to a stage doing some algebra where you see that you want an absolute value to be negative, well, you can just quit. That thing has no solutions. Which is the solution to the equation. The solution is there are none. Let's make that go smaller. All right, cool. So let's go back up here. So that means that absolute value of x plus 5 equals 10. The two things that could be in this absolute value are 10 or negative 10. That means you either have x plus 5 equals 10 or x plus 5 equals negative 10. Trucking along well enough so far? So we've turned a single equation into two. Do each of those equations look simpler than we had at the beginning? Yeah, that's progress, right? We're coming closer to solving. We have two things to do, but each of them is easier than the original. And in fact, in the time that I spent stalling, I could have just solved each of those. What do you need to do to either of those to solve? Yeah, get that 5 to the other side by subtracting. So, subtract 5 becomes, 5. 10 minus 5 is 5. Subtract 5 from this, negative 15. So it looks like x could be 5 or negative 15. Those of you who went ahead and just did it on your own, do you get the same answers? Nice. So here's a reasonable thing to be in the practice of doing whenever you solve an equation, especially if you care about having the right answer. Is there something we could do to check that this is correct? Let's plug these answers in for the original x and see what happens. And I think there's space right here to do that. All right. And maybe I'll go ahead and plug in x equals negative 15. We'll see what happens. I'll leave it to you to plug in x equals 5. We'll see if it works out correctly. So I would like to know, is the absolute value of negative 15 plus 5, absolute value, minus 7, equal to, I'll put a question mark there, 3. The like equal sign with a question mark through it isn't a standard notation, but I like to use it when I want to emphasize that I'm asking if an equation is true, not saying it's true when solving it or anything. So let's go ahead and go through and do it. Negative 15 plus 5 is negative 10, and that absolute value turns that into a 10. Minus 7, is that equal to 3? Oh, cool. And well, so that solution is actually a solution. What about x equals 5?
Yes.
Nice. Groovy. So with this remaining example, I'll give you all one of 3 options on it. I can talk through another example. You can go through an example and then we can see if we agree with what answers we get. Or it can be, no, I think those are the 2 answers. We're not going to see it. How many people would like me to talk through one more example? Okay, I will talk through one more example. Let's do it. Let's solve that equation. Absolute x minus 5 plus 2 equals 3. This looks like a pretty similar thing to what just happened, right? So let's use very similar steps. Whenever you want to solve an equation, you should look at the side that has the x's on it. Think about the last thing you do on that side. That's the thing you're going to undo. So what's the first thing we should undo on that equation? We should get rid of that plus 2 by subtracting 2. So subtract 2 from both sides. What does the equation become?
Value of x minus 5 equals 1.
Cool. Absolute value x minus 5 equals 1. Oh, neat. So this equation right here looks like absolute value of something equals a number. Absolute value of something equals a number. So, what can either that has no solutions, or I can break that up into 2 separate equations. What does that equation become if I do that trick to it? If I get rid of the absolute values? Excellent. Oh, I switched colors without meaning to. Cool. So I've now broken that up into 2 separate equations. Both of those look easy to solve. What do each of those individually become? No, this one becomes 6. That one becomes 4. And right, like, there's no, like, law saying that, like, the thing you write underneath a single one has to be the thing that corresponds to that one. But I think that's the most effective way to communicate. It would be confusing otherwise. All right, so it looks like we have 2 solutions, x equals 6 and x equals 4. Those of you who just did it independently, you get the same. How many people already went and plugged those back into the original and saw if they checked, saw if they worked?
Yeah, they work.
Cool. Let's do one different thing to check. Something that's maybe a little bit more mindless to do and relies more on computer-based computation. Could we have a computer graph that function? Yeah, and if you want to know when is a function equal to something, you like to know, like, when is the output value, the y value, equal to that? And we'll say that more formally later in the class, but oh, nice. By the magic of television, I've already, like, graphed this. So there in red, we see absolute value x minus 5 plus 2. I would like to know when is that equal to 3. So I've also graphed output equal to 3. And right, I happen to like Desmos as my graphing tool. You can't use it on exams, so if you're planning on it, I guess sorry. Right, because you would need a computer to do it. You can have a calculator, but not like an internet-connected device. Does this agree with those 2 being the solutions? Yeah. And in fact, there's one other thing we see here. Does it look like there are any solutions we missed? No. At least not between -10 and 10. Well, maybe you say, well, what happens if I go all like farther out? Look like there are any solutions we missed if I zoom out some? No. Cool. Alrighty. Looks feel pretty good. Nice. So maybe one quick reminder. There is an extra credit that is very similar to the problem we just did. If you like, just increased in complexity by 1 or 2 notches. This is maybe one of the easiest extra credits that I'm going to do. They're all given the same weight, so this is maybe low-hanging fruit if you want to do it. So, you might notice that I just like graphed a thing, and that involves like thinking about a pair of numbers x and y associated with a point on the plane. Let's formalize those ideas. Let's talk about Cartesian coordinates. So, the Cartesian coordinate system, the idea there is, if you can visualize just numbers as points on a line, you can realize pairs of numbers as points in 2-dimensional space on the plane. So let's start by drawing just a number line. I'll specify which point I want to call 0. Next, I'll draw a number line perpendicular to that number line. Those two things are perfectly perpendicular. It's a 90-degree angle. I won't have anyone tell me otherwise. So that they share the same origin. They both have the same 0. I'll call that point 0, 0. And what's the correspondence between points on a plane and coordinates? Well, let's talk about navigation. If someone says they're at the point 5, 3, what does that mean? It means you start at this origin, this 0 point. You go 5 to the right. You go 3 up. And you land on the point 5, 3. And you know what negative should mean too, right? If that 5 means go 5 to the right, then a -4 will mean go 4 to the negative right, to the left. There's the point -4, 2. Folks feel pretty good about that? How many people are offended by my inability to consistently scale this picture? Well, you maybe should be, but I'm not going to do any better than that. And maybe this is a note. If you find that you struggle to scale things consistently, maybe just label the points. Right? That is the point -4, 2. Now I know exactly what I mean by that dot. There are notations you add to this. These two axes break the plane up into 4 pieces, and I'll label them. Quadrant 1 is the set of all points, so things labeled x, y, where both the x value and y value are positive. So both of the coordinates are positive. And then I'll proceed counterclockwise. In quadrant 2, so if I have a point x, y sitting there, what can you tell me about those x and y values? X is negative. What can you tell me about y? Y is positive. Quadrant 3. Both are negative. Quadrant 4. Y is negative, and I guess your silence means x is positive. Nice. Cool. So you can coordinatize these things, and it's useful to have names for these various coordinates to describe where something lives. So something that will eat up a fair chunk of what I want to do with the rest of today's hour is going to be talking about distances between points in the plane. Let's try to compute some distances. So here's maybe an example. Here's the point -1, 1 and the point 2, 3. I guess the first question is, are those actually placed correctly? Are those actually the points -1, 1, and 2, 3? Awesome, cool. So I haven't made a mistake yet, at least on that front. Let's try to compute the distance. How would you compute that distance? Well, one fact you know is the Pythagorean formula, right? You know that if you have a right triangle, maybe it's worth drawing the picture. If you know that length and you know that length, then you know the hypotenuse. What does the Pythagorean formula say? And maybe I'll rewrite that in one further way. It looks like we eventually want the distance isolated. So we want that c isolated. So c is the square root of a squared plus b squared. So one thing this is a slightly tangential thing, that you might recall is that whenever you undo a square with a square root, you like introduce a plus or minus sign. Right? Like c could be plus or minus that square root. Why haven't I included the plus or minus here? It's a distance, so it has to be positive. So you're not worried about the negative option. Let's try to follow that algorithm here. So here's our right triangle. What's the length of the base of that triangle? 3. Why 3? Where'd you get that number?
2 to -1, the x coordinates.
Yeah, it's the distance between an x-coordinate of 2 and an x-coordinate of -1. That distance is 3. What's the height of the triangle? The height is 2. Awesome. Is that everything you need to use the Pythagorean formula here? Yeah, great. Do it. What's the distance between these 2 points? Square root 14. Nice. So there's an exact value. How many people, if they saw the square root of 13, would want to like take out a calculator if they wanted to get a decimal approximation? All right, cool. Well, that is an exact answer, and I didn't ask for an approximate value, so I'm happy enough. Folks feel pretty okay? Is the idea we just did, was there anything special about these points that made that work? No. You could do this with any set of points, and if you did that, you could get a formula. If you have any points in the plane, x1, y1, x2, y2, you can compute the distance between those 2 points as follows. The distance from the point x1, y1 to the point x2, y2 is the square root of the difference between the x-coordinates plus the difference between the y-coordinates. And I don't think I said squared. Both of those should be squared. Does that agree with what we did on the previous page? Did we compute the difference between the x-coordinates? Yeah, that was like the base of the triangle. Did we compute the difference between the y-coordinates? Yeah. Did we square them? And then take a square root? Cool, yeah. So it's exactly the same logic. We'll get you a general formula. And I want to use that general formula for something. So unfortunately, I left some of the physical things that I would have liked to bring to class today at home like a dunce. What I'd like to have done today is given each cluster of tables a tape measure, and then what I would have you do is determine the diagonal length of the various faces of this classroom. Now I don't have that, but I can think of an alternative. Do all the bricks in this room look like they're about the same size? So if I could maybe just ballpark how big any one of those bricks is, I could like count them up and compute some distances, right? So let's start with that. Maybe in particular, someone who's like seated close to a wall and feels reasonably brave in their idea and their ability to estimate distances up close. How big would you say those bricks are? 1 foot in length. I'll make that inches because probably you're not going to give the other dimension in feet. How tall would you say it is? 6 inches. And I don't know. If you disagree that those seem reasonable, which would be fair, keep in mind that I don't actually care about the validity of my final answer. This is entirely a toy example. I would have been happier to have a tape measure and we could like actually measure some things. I'm happy with that. All right, cool. So what do you think? Is that, with that information, let's determine at least like the vertical and horizontal dimension of these walls. And I guess let's do it by just counting up some bricks. Oh, and maybe that makes some things easier. All right, do I hear some quantities? 18 bricks across? Does that agree? I certainly haven't counted them. Okay. So I guess that would be called the width of the room. All right, how about the other two dimensions? How many? 17 high. And how many deep? 22? Anyone agree? Anyone disagree? 22.5? I'll stick at 22 because I want to leave the numbers easy. If I cared about this being precise, well, there are bits where I would have failed already, I think. All right, so I have these right now in number of bricks, but I have stated dimensions for each of these bricks. Each brick is 6 inches high.
Any chance you could put the screen?
Oh, yeah, thank you. Maybe I shouldn't be so definite with my ability to put the screen down. This was a while ago, but in fact, my first day teaching, my first class of that day, that thing fell off the wall when I tried to pull it down and almost hit me. That class went very poorly starting from then. No near-death experiences yet. All right, so let's make some computations. The width is 18 bricks across. I know that each brick is 12 inches per brick. The depth, those are also across 12 inches per brick. All right, so certainly those are not things that I would want to compute by hand. One could, right? 17 times 6 isn't so bad, but we have calculators, we may as well use them. I'm getting 102 inches for the height of the room. Oh, so how many people just knew you could do that already? If you go to like most search engines and type in a mathy looking expression, it'll calculate all right. Yeah, it's, I wouldn't say it's important, but it's convenient.
There was even a calculator on a specific website that could do most math equations.
Oh, yeah. So if you want like the most powerful version of that I know, go for Wolfram Alpha. Yeah, it can do lots. The trouble is that like it does too much sometimes, and it'll do things that, in the context of this class, we won't have justified.
Trivializes most things.
I wouldn't say that. Like having a computer that can do things that you would do algorithmically, like you can do that. That's true. But yeah, no, there are just some things that it would count as correct answers that I would say in the context of what we're doing as not correct answers. And we'll talk about those when we get to like logarithms, I think is the first instance. Let's do the rest. Those of you who happen to carry calculators around, this would be a fine time to bust them out if you want to use them and check my own answers, check my own values. I'm getting 216 inches for the width. And for the depth, $264. And all right, so let's prioritize a little bit. I think I'll compute one of the diagonal distances across, and then maybe I'll let you all do a remaining one. Which one should I do? Front, side, or top? I'll do the front. So, I know that the front of the room has a width of 216 inches. I know it has a height of 102 inches. For some value of the word no, I would like this diagonal distance. Yeah.
Can you just remove it?
Yeah. So far all I've done is I've labeled those two side lengths and I've drawn a diagonal. Is there a right triangle there we might take advantage of? Yeah, cool. Let's use this Pythagorean formula and compute that diagonal distance. So it looks like the front diagonal will be the square root of 102 inches squared. I'll suppress the inches because we know that everything's in inches right now. Plus 216 squared. And I don't know, how many people just have like memorized or internalized 102 squared and 216 squared and then the square root of their sum? Yeah, fair, right? Let's compute that using a machine, right? We could compute a lot of that by hand if we wanted to. $102 squared plus 216 squared. And let's talk about rounding. So there's nothing objective in this problem description that says like how much precision I want in my final answer. So let's just be like reasonable about it. Based on what I've done so far, do you think, would you trust the number that I just gave even up to the inch? Oh, okay. I don't know if I would. Because like step one is eyeball that book and tell me what its dimensions are. I wouldn't trust that up to an inch. I wouldn't be surprised if those measurements were off by an inch, and then those will propagate as we go through it. So I'd probably only be confident of this really up to the tens of inches. So don't go beyond what you know is reasonable, and then just, when in doubt, communicate more. If you're writing this up and this is your answer, you can say, I'm rounding off to the nearest inch. Neato. Folks feeling pretty good? How many people have already determined some of the other diagonals? If not, pick a diagonal, determine it. I will come back in like 2 minutes and ask. Oh, and you're allowed to like walk with each other right now. It's not like this is a test. So if like you're using a cell phone calculator, but the person next to you has like a real calculator, you don't have to do the plugging in of the numbers. You can compare the exact values and then get the decimal approximations. All right, at this point, in the interest of time, though, so what is the diagonal length of the side wall? About 283 inches. Anyone agree or disagree? Anyone disagree? Anyone agree? Awesome. Then I believe it. And I, of course, didn't do it because I was just standing here. You saw me not doing any arithmetic. What about the ceiling? About 341 inches. Does that agree? Awesome. Cool. So, the thing that I think that I'll pick up on next time, and something that might be worth thinking about, is try to reason through. We've done lots of measurements. Surely we have enough information to compute the distance from that point to that point, from corner to opposite corner to opposite corner. Find the diagonal measurement of the room. And we'll do that bit of calculation next time, tomorrow. But maybe think about that a little bit. Oh, neat. I'm even ending class early by 40 seconds. That's not going to happen much.
Well,